Welcome to another deep dive.
Oh, nice.
Yeah, today we're going to be exploring quantum physics.
Right.
But trust me, it's going to be fascinating once we sort of peel back all the layers of the onion, so to speak.
I think a lot of people are intimidated by the subject.
I think so too.
Hmm.
And so we're using John Gribbin's book, In Search of Schrodinger's Cat.
Oh, sure, yeah.
As our roadmap for this.
That's a classic.
It is a classic. He's really a master at making complex ideas accessible.
Yeah.
So think of this as kind of like quantum physics for the curious.
That's an apt title, I think, because it challenges our everyday perceptions of reality.
Exactly.
And reveals a universe that operates in ways that often defy our intuition.
And it's true. Instead of getting bogged down in all these, really complicated equations, we're just going to focus on some of the core ideas.
Sure.
What they mean, how they were discovered, and then kind of what they tell us about the universe and our place in it.
Right.
Did you know that even Isaac Newton, back in the 1600s, was grappling with some of the early clues that would lead to this quantum revolution?
Yeah, I mean, Newton's work on the nature of light was groundbreaking, but also contained the seeds of a mystery that wouldn't fully unravel for centuries.
Okay, so let's rewind back to Newton's time.
Okay.
What was it about light that hinted at these strange things to come?
Like many scientists of his era, believed that light was made up of tiny particles, which he called corpuscles.
Okay.
And this theory explained some aspects of light's behavior, like how it travels in straight lines and bounces off surfaces.
Okay.
But it couldn't account for everything. For example, there was the phenomenon of light diffracting or bending around obstacles, which suggested a wave-like nature.
Ah, yes, the classic wave versus particle debate.
Right.
It's interesting how these early scientists, these early discussions, kind of set the stage for what we're going to get into about quantum mechanics.
Exactly. And that's where the double slit experiment comes in. It's one of the most important experiments in the history of physics.
Wow.
Because it reveals a fundamental truth about the nature of light and, by extension, about the nature of reality itself.
Okay, so this experiment, we've got a beam of light.
Right, imagine this,
We've got a screen.
Have a beam of light.
And there are two slits.
Yeah, a screen with two
tiny holes.
Narrow slits cut into it.
In it.
Right.
You shine the light through the slits.
Shine the light through the slits.
And you would expect to see two bright bands.
And you'd expect to see...
on the screen behind,
two bright bands on the screen placed behind the slits.
Yeah, like that's kind of, that's how light works.
Seems logical, right?
Yeah.
However, what you actually see is a pattern of alternating bright and dark bands.
Wow.
An interference pattern.
Good.
As if the light passing through each slit is interfering with itself, like waves do.
So it's almost as if the light knows that there are two slits.
Exactly.
It's like, okay, well, I'm going to
it's
do this wave thing.
Of the two slits.
Yeah.
Even though it shouldn't be, right?
So light acts like it's a wave.
So light is acting like a wave in this experiment.
But what about then the particle idea?
The particle thing. Right. How does that fit in?
Yeah, where does that fit in?
That's the truly mind-boggling part.
Oh, okay.
So if you dim the light so that only single photons are being emitted, you would expect to see individual dots on the screen, right?
Yeah.
But over time, even with single photons, the same interference pattern emerges.
That's so strange.
Meaning each individual photon somehow goes through both slits simultaneously.
Wow.
And interferes with itself like a wave to create the pattern.
Now, that's just bizarre.
It is bizarre.
A single particle going through two slits.
It's not how things work in our everyday world.
It's not how anything works.
Right, precisely.
That's not how my car works.
No, but it demonstrates wave-particle duality.
Yeah.
Light isn't just one or the other.
Right.
It's both.
It's both, yeah.
Depending on how we observe it, it can exhibit the properties of either a wave or a particle.
So light is playing tricks on us.
It seems that way.
Changing its behavior depending on how we look at it.
It's depending on how we set up the experiment.
Yeah, that's amazing.
Yeah.
So, I mean, what does that tell us?
It suggests that our classical notions
about reality,
of what's real and how things work,
if something as fundamental as light can behave this way,
don't hold up at the quantum level.
Yeah.
It brings into question our assumptions about the nature of observation and its role in shaping reality.
Wow. Okay.
But
it gets even stranger.
I can't get any stranger.
Oh, it can.
Oh, no.
Not only does light exhibit this duality, but matter itself can exhibit wave-like properties as well.
Wait, hold on. You're saying that things we can touch, like a baseball or even a person, can also act like waves.
This is a fundamental principle of quantum mechanics.
Okay.
Everything, from light to electrons to atoms,
can exhibit both wave-like and particle-like behavior.
Wow.
And this wave-particle duality is really a cornerstone of understanding the quantum world.
Okay, I need a minute to wrap my head around that one.
It takes some getting used to.
But while I'm doing that, can you tell us more about this observer effect you mentioned? It sounds like the very act of observing something.
That's the crux of it.
Changes how it behaves.
The double slit experiment gets even weirder when you try to determine which slit each photon goes through. As soon as you try to observe which path the photon takes, the interference pattern disappears.
Wow.
And the photons behave as if they are only particles again.
So trying to observe the photons forces them
you're forcing them to
choose a path, losing their wave-like behavior.
Yeah, and it loses that wave-like behavior.
Oh, man. This quantum world is full of surprises. But
it is full of surprises.
I can see why some physicists, even Einstein, found this whole thing unsettling.
It's very unsettling.
It challenges everything we thought we knew.
Yeah, it challenges everything.
About how the universe works.
Yeah.
Yeah, it's almost as if the universe is aware of our observation.
Right.
And changes its behavior accordingly.
You've hit on a key point.
Yeah.
The role of observation in quantum mechanics.
Right.
It has been the subject of intense debate and interpretation for decades.
Right.
What constitutes observation?
Yeah.
Does it require consciousness?
Right.
These are questions that physicists and philosophers are still grappling with today.
Yeah.
But even more perplexing is the fact that our ability to know things about these quantum particles is inherently limited.
Okay.
You're talking about Heisenberg's uncertainty principle now, right?
Yes.
The one that says that we can't know everything about a particle.
Right.
With perfect accuracy.
Yes.
That we can know its position or its momentum.
Yeah.
But not both at the same time.
So it's not just a matter of having better instruments.
Exactly. It's a fundamental limit on what we can know.
Okay.
And this is a crucial point to understand. It's not about our technology being inadequate.
Right.
It's a deep principle woven into the fabric of the universe.
Okay, I'm starting to see why this is so revolutionary.
Yeah.
It just throws out our classical deterministic view of the universe.
It really does.
It's like the universe is saying to us, you can know this or you can know that, but you can't know everything.
You can't know everything.
It's like trying to juggle too many things at once.
It is.
And something always ends up falling.
That's a great analogy. And just as you can't perfectly grasp every object you're juggling, we can't pin down all the properties of a quantum particle simultaneously.
It's a cosmic trade-off.
It is.
This is absolutely fascinating.
It is.
And I'm sure our listeners are just eager to hear more.
Yeah, I'm sure they are.
So let's dive into the implications of all this in our next segment.
Sounds good.
I'm still trying to wrap my head around this idea that even something as solid as like a baseball has wave-like properties. It's just so strange. It's like the universe is constantly reminding us that there's more to reality than...
There is. And speaking of things that challenge our everyday perceptions, let's delve a bit deeper into Heisenberg's uncertainty principle.
Right.
It's not just a quirky scientific fact.
Right.
It has profound implications for our understanding of the universe.
We touched on it earlier, but... I think it deserves a little more attention.
A little more attention.
So just to recap, it's not just that our instruments aren't good enough, right?
Right, exactly.
It's like there's this fundamental...
There's a fundamental fuzziness built into the fabric of reality.
Built into the fabric of reality.
At the quantum level.
At the quantum level.
Yeah.
So you're saying even if we had like infinitely precise instruments...
Even if we had infinitely precise instruments...
We still couldn't know...
Both.
We still couldn't know...
The particle's position.
Both the particle's position...
Or momentum.
and momentum. With perfect certainty.
With perfect certainty.
It's like the more precisely you try to measure one, the less you can know about the other.
So it's like we're gaining knowledge about one aspect, and then we're losing information about the other.
It's a cosmic trade-off.
It's a cosmic trade-off.
We gain knowledge about one, but lose information about the other.
And so does this have any practical implications?
Absolutely.
Beyond, like, the subatomic world? It's not just a theoretical curiosity.
Okay.
The uncertainty principle has real-world consequences.
Okay.
For example...
Give me an example.
It helps explain why atoms don't collapse.
Oh, okay.
The electrons orbiting the nucleus are subject to this uncertainty, so their position and momentum can't be precisely defined. Okay. This inherent fuzziness prevents them from just spiraling into the nucleus.
So the uncertainty principle is actually responsible for the stability of atoms.
It is.
And therefore, like, the existence of matter.
And therefore the existence of matter as we know it.
That's huge.
It's pretty profound.
That is profound.
And it gets even more mind-boggling when you consider how this principle might play out on a larger scale.
All right.
Like, if we can't precisely define both the position and momentum of even a single particle, imagine the implications for complex systems, like weather patterns or the stock market.
That's a lot to ponder.
It is a lot to ponder.
It suggests that, like, prediction and control may have fundamental limits. Even with, you know, perfect information.
Even with perfect information.
But before we get, like, too lost in the philosophical implications of all this, I have to ask about Schrodinger's cat. I mean, it's such a...
It's a classic.
Famous thought experiment.
It is.
But I'm still not entirely sure I understand it.
Okay.
Like, what is it trying to tell us?
Schrodinger's cat is a way of illustrating the concept of superposition, one of the most bizarre and counterintuitive ideas in quantum mechanics.
Okay, so what is superposition?
So imagine a cat sealed inside a box with a device that has a 50-50 chance of releasing a lethal poison.
Okay, I'm already feeling bad for the cat.
Yeah. According to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states.
Okay.
Both alive and dead.
Hold on.
It's not that we don't know which state it's in.
Yeah.
It's that it's in both states simultaneously.
How can something be?
I know, it defies logic, right?
Both alive and dead at the same time.
It certainly does defy our everyday experience, but that's the point.
Okay.
Schrödinger wasn't suggesting we actually do this to a cat.
Right. Of course not.
He was using this thought experiment to highlight the strange implications of quantum superposition.
Okay.
So the cat's fate is entangled with the state of a quantum particle, which can exist in multiple states at once until it's measured.
So you're saying the cat is in some kind of, like, limbo.
It's in a superposition of states.
Until we look inside the box.
Until it's observed or measured.
So what constitutes looking in this scenario?
That's a great question, and it gets to the heart of the debate about the role of observation in quantum mechanics.
Right.
Some interpretations argue that it's the act of measurement of interacting with the system that collapses the superposition and forces a single outcome.
Okay.
Dead cat or live cat.
So our interaction with the system somehow determines reality.
It raises profound questions about the nature of reality and the role we play in shaping it.
It's a bit unnerving.
And it leads us to another mind-bending phenomenon that Gribbin discusses.
Okay.
Quantum entanglement.
Ah, yes, entanglement.
The spooky action at a distance.
Spooky action at a distance.
Yes.
What exactly does that mean?
So imagine two particles.
Okay.
Linked together in such a way that their properties are correlated no matter how far apart they are.
Okay.
If you measure the state of one particle, you instantly know the state of the other, even if they're light years away.
You're saying that something I do to one particle can, like, instantly affect another one on the other side of the universe.
Even on the other side of the universe, potentially.
That's got to be.
Yeah, it appears that way, doesn't it?
Faster than the speed of light.
Which is why Einstein famously called it spooky action at a distance, because it seemed to violate one of the fundamental principles of his theory of relativity.
Yeah, that nothing can travel faster than light.
That nothing can travel faster than light.
So how do we explain this?
That's one of the biggest mysteries of quantum mechanics.
How can two particles be so interconnected?
Yeah, it suggests a level of interconnectedness
so entangling.
That we're only beginning to understand.
Yeah.
It's as if the universe has these like hidden connections, unseen threads that tie everything together in ways we can't fully comprehend.
Okay, so light acting as both wave and particle.
Yeah.
A fundamental limit to what we can know.
Yeah.
A cat that's both alive and dead.
Uh-huh.
And particles linked across vast distances.
Yes.
What does it all mean?
It's a lot to take in.
How does this quantum weirdness relate to us?
That's a great question, and it's one we'll explore in our next segment.
All right.
Because while quantum effects might seem confined to the subatomic world,
right,
they have profound implications for our understanding of the universe and our place in it.
I can't wait. Okay, so we've covered some truly mind-bending concepts in this deep dive.
We have.
It's hard to believe.
It really is.
That the universe operates in such strange ways.
Yeah, it's strange.
Especially when
it is.
Our everyday life seems so normal.
Yeah, well, that's the remarkable thing about quantum mechanics is that its effects are most pronounced at the subatomic level.
Okay.
A realm far removed from our macroscopic world.
Right.
But here's the fascinating part.
Okay.
Even though we don't see objects teleporting or, existing in multiple states simultaneously, quantum phenomena underpin many of the technologies we rely on every day.
You're saying that our everyday world
in a way
is secretly influenced by this quantum weirdness.
Our everyday world is secretly influenced by quantum weirdness.
Give me an example.
Okay, so take lasers.
Okay.
I mean, they're used in everything.
Yeah.
From barcode scanners at the grocery store to fiber optic communication networks that carry vast amounts of data across the globe.
Right.
The very principle that makes lasers work, the precise and coherent emission of light, is rooted in quantum mechanics.
Okay, so something as simple as, like, scanning groceries relies on
these principles discovered, these principles of quantum mechanics.
By delving into this bizarre world.
Yes.
That's incredible.
That is incredible.
What about, what other technologies?
So you mentioned quantum computing earlier. So quantum computing is perhaps the most exciting frontier where quantum mechanics is really poised to revolutionize our world.
All right.
So while traditional computers rely on bits, which can be either 0 or 1.
Right, 0 or 1.
Quantum computers use qubits.
Qubits.
And these qubits can exist in a superposition of states, being both 0 and 1 simultaneously.
Okay.
Thanks to the principle of superposition.
Right, which we talked about.
I talked about earlier.
If I'm understanding this correctly, this means that quantum computers can, like, perform calculations in ways that are
fundamentally different. From classical computers. It's like they can explore multiple possibilities at once.
Which would make them, like, incredibly powerful.
Right.
For certain
really powerful types of problems.
For certain types of problems.
Yes.
Exactly. Quantum computers have the potential to crack encryption codes.
Right.
That are currently unbreakable.
Oh.
Simulate complex molecules for drug discovery.
Right.
Revolutionize materials science. Help us understand the universe in new and profound ways.
It sounds like quantum computing.
It's a game changer.
It is, like, on the verge of unlocking,
it is on the verge of unlocking incredible possibilities.
Yeah. But beyond technology, how does quantum mechanics, like, change our understanding of reality itself?
It forces us to rethink some fundamental assumptions.
Okay.
You see, in classical physics, the universe is seen as, like, this giant clockwork mechanism.
Right. Yeah. Everything is deterministic, predictable, and the observer is separate from the observed.
Separate from the observed.
Quantum mechanics, on the other hand, introduces an element of chance.
Okay.
Uncertainty.
Okay.
And it blurs the line between the observer and the observed.
So instead of a clockwork universe...
Yeah, it's more like
a cosmic dance.
Cosmic dance.
Where, like, relationships and interconnectedness
exactly.
play a central role.
That's a beautiful way to put it.
I think so. It's really...
Quantum mechanics suggests that the universe is this vast interconnected web where particles can be entangled across vast distances and where the act of observation can influence the outcome of events.
Right.
It's a far cry from the deterministic clockwork universe of classical physics.
I think it's both humbling. It is humbling.
And empowering and empowering.
At the same time.
Yeah.
Humbling because
it reminds us that
there's so much we don't know and perhaps can never fully know.
We don't know everything. Yeah. And we can't know everything.
Yeah.
And it's empowering because...
it
kind of suggests that.
It suggests that we are not just passive observers.
Yeah.
But active participants in shaping reality.
Our exploration of John Gribbin's In Search of Schrodinger's Cat.
Yeah, it's been quite a journey.
Has certainly been a mind-expanding journey.
It's been mind-expanding.
We've encountered these concepts that just defy, our everyday understanding.
Huh. But in doing so, we've kind of caught a glimpse.
Of the
universe's breathtaking complexity.
And interconnectedness. And if there's one thing I hope our listeners take away from this deep dive, it's a sense of curiosity and wonder.
Yes.
The world of quantum mechanics is still largely unexplored.
Right.
And who knows what incredible discoveries await us in the future.
For one, I'm eager to keep learning.
Me too.
And exploring.
Yes.
So to our listeners,
we
encourage you to
definitely
pick up Gribbin's book.
Pick up the book.
And embark on your own journey.
Yeah.
Into
the quantum world.
The quantum world.
It will challenge your assumptions. It will leave you with a sense of awe at the mysteries of the universe.
Until next time.
Yeah.
Keep those minds curious.
Yes.
And open to the wonders that lie beyond our everyday perception.
Wonderful.